So let's have some more fun with power series. If you remember back to Calc 2, we talked about Taylor polynomials and Maclaurin polynomials, and we said we could take some functions that had things that were infinitely differentiable, which means that we could take the derivative of things over and over and over and over again. And we can represent those in terms of a Taylor series or a Maclaurin series. So we're talking about functions like e to the x, because if we were to take successive derivatives of e to the x, we would just get e to the x. Or if we took derivatives of sine or cosine, derivative of the sine is cosine, derivative of the cosine is negative sine. So those derivatives are always kind of bouncing back and forth between sine and cosine. It's not going to lead to zero in any way. ln of x was another one that we could take derivatives of. We also saw derivatives like arctan, just anything that we could take derivatives of, and we're looking for something that doesn't go to zero. We can express some polynomials in terms of Maclaurin and Taylor series. We're not going to talk about those. We're going to focus on these. These are more like your transcendental functions. So, and in fact, any combination thereof, like e to the x times ln of x or e to the x times sine of x, we can represent those as Taylor series or Maclaurin series. So remember the difference between Taylor and Maclaurin. Maclaurin series are always going to be centered at 0, whereas a Taylor polynomial is going to be centered at some value called c. And what we can do is we can create this Taylor polynomial and write out a few terms in that polynomial, and it's going to be a really nice approximation for whatever that curve is around the center. That's an important piece. I can't forget that. So around that center, it would be a really nice example. So I want to dive into that a little bit more before I jump into this Maclaurin series for e to the x squared. Just to give you a better idea of what we're doing here. So just for fun, let's talk about e to the x. So we know what e to the x looks like, right? E to the x is our exponential function, looks like this guy. If we look at our table of polynomials, here's your Maclaurin series. So I'm going to write out just a few terms here. If n is 0, then we're going to have x to the 0 over 0 factorial. If n is 1, we would have x to the first over 1 factorial. If n is 2, we're going to have x squared over 2 factorial. I'm just going to write out a few. And x is 3, x cubed over 3 factorial, if n is 3. So this guy, 0 factorial has a special definition. 0 factorial is actually equal to 1. And we know x to the 0 is 1, so that first term is just 1 there. And then we have x over 1 factorial, which is x. And then we have x squared over 2 factorial, which is 2. We have x cubed over 3 factorial, which is 6, and then so on. So what a Taylor or a Maclaurin polynomial does is it models the behavior of this function at wherever that center is. And since this is Maclaurin, the center is at 0. So around our x equals 0, this guy will look really close to this. Now, end behavior is going to be different, but around that center, it should lay pretty close to being on top, if not on top of that curve. So let's graph this in Desmos so you can see what this is doing. So we're in Desmos, and we're going to graph both of those. So we've got e to the x. E to the x is our exponential function. It's this red curve. So we're going to start building that polynomial on top of it. And we only came up with 4 terms, but look what happens to this as we add more terms. So we've got 1 plus x. So you can see that graph. That's not a very good model of that red curve, but it is touching that graph at 0. But if I add the next term, which was x squared divided by 2, now you can see how that blue curve is really closer to that red curve at 0, which is the center. Let's add the next term. It was x cubed over 6. So you can see how this is becoming a better fit for that exponential function. And if we were to add another one, I'm just going to add one just for fun, even though we only came up with 4 on the other sheet. Our next one would be x to the 4th. Oops. X to the 4th divided by 4 factorial, which would be 24. So you can see, I'm going to change this graph and zoom, how this polynomial is laying right on top of that red one. And it's modeling that exponential function really well. So why would we want to do this? Well, sometimes polynomials are just nicer to deal with than some kind of transcendental function. So, the more terms we add to this series, the better that polynomial will model that transcendental function. And we can see that as we added terms. The first 2 terms didn't give us a good graph at all. But once we started adding the 3rd term, the 4th term, and the 5th term, we're getting really close to, we're getting a better approximation of what's going on with that red graph the more terms we add, which expands what's going on with that blue graph. So that's all a Taylor or a Maclaurin series does, or a polynomial does, is that it models that graph. And it's really focused on that center, where that center is and what that model is going to look like. So we do have a table of basic Maclaurin series over here. This is from your textbook. I'll provide this for you in Blackboard. Notice it's giving you a few terms. It's telling you what the series is going to look like, and it's giving you the interval of convergence here, which is nice. And what we want to do is we can use this table to actually build other series for other transcendental functions. So let's look at a few examples. Suppose we want to find the Maclaurin series for e to the x squared. So let's start with what we know. We know what e to the x looks like. E to the x we had 1 plus x over 1 factorial plus x squared over 2 factorial, x cubed over 3 factorial. And we can write that concisely as this. And that guy's an exponent. We want to derive a Maclaurin series for e to the x squared. So all we really want to do is replace this x with an x squared. And that's going to require us replacing all of these x's with an x squared. And then we'll see how we'll be able to rewrite that. So if we do that here, I'm writing the expansion out first. So I'm replacing that x with x squared. So now I have x squared quantity squared over 2 factorial. And then x squared cubed over 3 factorial. So I'm going to simplify this expansion. So if we wanted to write that in terms of a summation, we have x squared to the n, replacing this x, over n factorial. And you can see what this series will look like. This is x to the 2n. Power to a power, we multiply the powers. Now, I always like to double check to make sure this guy's going to work. So if I were to plug 0 in, do I get the first term? So we would have x to the 0, which is 1, over 0 factorial, which is 1. So we would get a 1. If we substitute in 1, our exponent on x would be 2 over 1 factorial. So it gives us that second term. Let's do the third one, just for insurance. If we substitute in 2, we're going to have x to the 4th over 2 factorial. So you can see how this guy is giving us the polynomial that we have. So there is our Maclaurin series for e to the x squared. It just required us taking what we know and replacing it with a substitution for x. And in this case, our substitution was x squared. Now, let's do a different one. Let's do a Taylor series. We want to find a Taylor series of ln of x, and we want it to be centered at 1. So let's look at what we have. If we look in the textbook at the table of Maclaurin series, we do have ln of 1 plus x. So let's write that out. You're always going to start with what you know. So there's what we know. Now keep in mind what we want. We want a Taylor series centered at 1. So we kind of know what we want this to look like. We want this to look like, instead of an x, we want an x minus 1. Remember, to be centered is going to be x minus a, but we want our a to be 1. So we want that. So we know kind of what this guy's going to look like. Replacing that x with x minus 1. So check out what's going to happen here. If we do that here, I'm going to recopy so everything's on the same line. So we replaced x here with x minus 1. We're going to have to do the same thing here for that expansion. So just so you can see a few terms, just replacing all of these with x minus 1. So if we were to do that, we're going to have an x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4. So you can see what this guy would look like. And we can make sure that these match up. If we plug in n is equal to 1 in here, then we're going to end up with a positive over 1 times x minus 1 to the first. So we get that first term. If we were to substitute in 2 into this series, we're going to have a negative 1 over 2 times x minus 1 squared. So we get that second term. So you can see that this guy does give us that, which makes sense because we started with what we knew up here, which is good. And we said that all of this ended up being the ln of 1 plus x. But if I replace that x with x minus 1, then this is giving us an ln series for x, which is what we wanted. So it's all about taking what we know and trying to tweak it in terms of what we want. We wanted something for ln of x centered at 1. So we did that replacement knowing what x was going to have to be replaced with. Now, let's talk about how this is going to shift that interval of convergence. So the interval of convergence for ln of 1 plus x was from negative 1 to 1, and that came straight off of the chart that we have. Looking at this line, there's our interval of convergence, negative 1 to 1. So if we replace x with x minus 1, that x minus 1 is going to shift this graph to the right 1 unit, which means it's going to shift that interval to the right 1 unit as well. So if I take this negative 1 to 1 and I pick it up and I move it to the right 1 whole unit, negative 1 is going to go to 0, positive 1 is going to go to 2. So then our new interval of convergence, without having to go through that ratio test, without having to test the endpoints, we can just think about this in terms of transformations, going way back to 171. If we take a function and we replace with x minus h, we know that's a shift to the right h units. So all that stuff from 171 is actually coming back and helping us create some shortcuts for finding that interval of convergence based on what we know and what we are replacing x with. Likewise, if we needed to replace x with x plus h, that moves left. So for this guy, we replace with x minus 1. That's going to shift this right 1 unit, which takes that interval and it shifts that 1 unit also. So there's our new interval of convergence. We could go through, we could use the ratio test, we could test endpoints, and we would get the exact same answer. So it's pretty cool how we can start seeing that combination of classes playing into this one class. And we're combining all this knowledge into one problem.